Hi. The adult makes approximately 10 billion white blood cells every day, about 400 billion platelets every day, and about 200 billion red blood cells in a process known as hemopoiesis, or blood formation. This process starts off in fetal development in the yolk sac, which is the primary blood forming tissue, but cells of the yolk sac leave the yolk sac and colonize other tissues in the body, which then develop the ability to form blood. For instance, the liver, the spleen, the thymus, the bone marrow. I'm probably forgetting something, tonsils. A lot of these have blood forming abilities. Some of them end at birth, such as in the liver, which doesn't produce blood anymore after birth. And by the time we reach adulthood, the only blood forming tissue we have left is the red bone marrow, and we don't even have that in all of our bones. Now, the cell that's responsible for the formation of all the formed elements except platelets in the body is found in the red bone marrow and is called the pluripotent stem cell. Pluri means many, potent means the potential to become. So this stem cell has the potential to become or give rise to every kind of blood cell in the body. It gives rise to neutrophils, basophils, eosinophils, monocytes, lymphocytes, and even a precursor to erythrocytes called the erythroblast. We're going to talk in much more detail about the white blood cells when we get to the immune system, especially the neutrophils, which are the most abundant and play a very important role in the initial response to an infection. But we'll also mention basophils and eosinophils. Monocytes we won't hear much about because they only last in the bloodstream for a few days. After a few days, they leave the bloodstream and they become a cell known as the macrophage, or the big eater. And we'll see that one playing a huge role in the immune system when we get there too. Lymphocytes are not just one flavor, they come in several. We have B lymphocytes, T lymphocytes, and natural killer cells, and we're going to see all of those playing important roles in the immune system. But the cell that I want to focus on right now, and its particular life cycle, or life pathway, is the erythrocyte. Now, by the time we get to the mature erythrocyte, we have a cell that no longer has a nucleus. I know you probably can't tell from my drawing, but this is supposed to look something like a Lifesaver candy, except that the hole doesn't go all the way through. We say that it is discoid shaped. So it looks kind of like a donut that there's no hole all the way through. It's just thin in the middle. Now, the way this starts out is that the pluripotent stem cell produces a precursor cell known as the erythroblast. Whenever you see blast in a cell, that means that it's a precursor. It is building up to the final mature version of the cell. Now, the erythroblast eventually becomes a reticulocyte. What it does in that process is it loses the nucleus, and we're going to talk about why it's so important that the red blood cell loses its nucleus shortly. But it loses its nucleus, and its endoplasmic reticulum becomes super overdeveloped and starts producing gobs and copious quantities of the protein hemoglobin, which has the responsibility for carrying oxygen in our red blood cells. So reticulocytes lack a nucleus and are red in color, but they're not yet disc-shaped. They're still, the endoplasmic reticulum and probably some of the nucleus components are still being broken down, and it still has a sphere shape. But the reticulocyte is what enters into our bloodstream, and then within a few days it matures and becomes an erythrocyte. This is important because we can tell something about how rapidly someone is forming blood by the percentage of reticulocytes in their blood count. If we see a high percentage of reticulocytes, that means that their marrow is making blood at a faster rate than what we normally expect. If we don't see an average number, or we see a lower than average number of reticulocytes, then it tells us that that person is not manufacturing blood at the normal rate. And this can give us information about health and disease.